Hello, I'm Jack Michael. This is Physics 2211, Lab 5. Here's a brief table of contents. First, we'll cover introduction, data observation and models, code discussion, and then finally conclusions. Introduction. This lab is being conducted with the purpose of seeing how a spring falls when stretched, to see if it falls all at once or when attaining the relaxed length. The fundamental principle at work here is Newton's second law, otherwise known as the momentum principle. Preview of the results. The bottom of the slinky does not start to move until the top of the slinky reaches it. Newton's second law. As I discussed, this is the main principle that's being looked at here. Newton's second law, known as the momentum principle, states that the force is equal to the change in momentum over time. Over the change in time. It indicates changes in movement within the system and its surrounding. Procedure. Download a video of the slinky falling and upload it to the tracker software. Use the center of mass, calibration stick, and axes to properly record the fall data frame by frame. Create a computational model to prove the spring does not move until the top reaches the bottom, and 4. Compare the computational model and the tracker data and its relation to Newton's second law. As you can see, here's the clip of the slinky falling, and on the right is the tracker data for the mass and the y position, or the y position on the y-axis and time on the x-axis. Observations. Start time started at 0 seconds, end time at 0.767 seconds. Initial velocity, the 0 vector, and initial position also the 0 vector. System and its surroundings. The system in this case is the slinky, and the surroundings are anything else that affects it, being air or gravity. These observations will be used to see the impact of gravity on the object's motion. Code. The movement model, I added initial conditions of the 0 velocity and position. Put in net force equations, tension equation, and gravity equation. As you can see to the right here. Here's more of that code right here. Yeah. Here's the outcome of this. So on the left is the actual graph of the center of mass of the slinky, and on the right is the computational model of this. As you can see, they match pretty closely, having the same basic general shape. Potential errors. Mistakes could have been made while using the tracking software. Additionally, in the video model, it would be possible to not have drag interacting with the falling object. Conclusion. The momentum principle, Newton's second law, is observed in the video through the object's acceleration, mass, and force interaction. Force grows as mass grows, the same with acceleration. This experiment proved that a slinky bottom only moves after it restores its relaxed length. The gravity and drag computational model is near exactly like the experimental video model of the movement of the slinky being dropped.
We